Okay, yeah, well, welcome back, everyone. Thanks for coming. I'm going to kick off our talks this year with this talk on scalar curvature entropy and generalized Ricci flow. Please feel free to interrupt whenever you want. So I just want to start by recalling some fundamental estimates for Ricci flow. That sort of guide all of our understanding of the singular sets pretty much for Ricci flow. So here we have just the usual Ricci flow. So dg dt is minus twice Ricci. And throughout this talk, I'll let box denote the heat operator. So this is ddt minus the time-dependent Laplacian. And yeah, so the first key estimate you learn for Ricci flow is that if I apply the heat operator to the scalar curvature, you get twice norm Ricci squared. And by the maximum principle, you know that the minimum is increasing, at least weakly. And you also get sort of a rigidity result out of this. You know, if your initial scalar curvature is non-negative, then either it's Ricci flat, or there exists a metric with strictly positive Ricci curvature, just given by any forward time evolution of the Ricci flow. So this is very, very fundamental point for Ricci flow, and is kind of well related to these estimates of Perelman in the following way. So we can define also this conjugate heat operator box star, which I just recall. So the definition, this is just minus ddt minus the time-dependent Laplacian plus the scalar curvature. And it's more or less defined so that the following basic formula holds. So if I take the time derivative along Ricci flow of the integral of two functions against the volume form, you get the integral of box u times w minus u times the conjugate heat operator acting on w. So this is the sense in which it's conjugate. And yeah, so this operator plays an important role, and already it's kind of linked in a way to this first fact, because somehow you have this like reaction term for this operator, but you have this a priori lower bound for it. Okay, so you know it's bounded below. So again, this one-sided bound plays some important role in the analysis. But you can use this conjugate heat operator to define these other monotone quantities of Perelman. So for instance, I say U solves, so if I take a solution to this conjugate heat equation, and I define U is e to the minus f, then I get a further sort of kind of like a scalar curvature monotonicity, but I need one more definition here. So I'll define R upper F by definition. This is the scalar curvature plus twice Laplacian f minus norm gradient f squared. I'll call this weighted scalar curvature. So I guess this has some motivation coming from math physics, but for our purposes, you can also, so one appearance of the scalar curvature in Riemannian geometry is in the Bochner formula for spinors. And if you sort of compute that Bochner formula, but instead of using the Riemannian volume form, you use a weighted volume form, weighted by e to the minus f, then the reaction term takes this form. So this is why I call it weighted scalar curvature. So sort of related to weighting the volume form. And also, while I'm at it, yeah, so another definition we need, so Ricci F by definition is the standard Ricci plus Hessian F. This should really, well, it's kind of like weighted Ricci curvature, but this is this Bakri-Emery Ricci. Okay. So, okay, sorry, yeah. So with this notation and then with these definitions, you get the following formulas of Perelman. So you take the box star of RFU. And what you get is minus twice norm the F Ricci squared times U. This is sort of underlies what could be called like the steady Harnack estimate. But in any case, there are some various estimates that follow immediately from this formula. And also this implies, this is sort of stronger than, this implies like the monotonicity.
And so this is true provided the equation above all, right? That it's like...
Yes, yeah, sorry, like pretty much always well, actually that's, you will satisfy some kind of backward heat equation like this, yeah. Yeah, but it's very much necessary, yeah, for all of these appearances of F and U, yeah. Does that answer it?
Yeah, thanks.
Okay, yeah. So this also gives the monotonicity of this F functional, which of course is, maybe just a second. This functional is usually written as R plus norm grad F squared e to the minus F dVg, but of course, what it actually is by some elementary integration by parts is just the weighted scalar curvature integrated against the weighted volume. Okay. So basically putting together, it's just an elementary point, putting together this basic fact with this formula, you get the monotonicity of this F functional. Okay. And then sort of going further, there are these what I'll call the entropy integrand. So WF is tau times RF plus F minus N. Where here, you basically in context, always, you think of a Ricci flow, where should I write it? You think of your Ricci flow as existing on like 0t, and then this tau, it doesn't really have to be like this, but tau is basically time to a singularity. This is almost always how it gets used, more or less. So it's this scalar curvature, but with some further weighting by time, and then the density appears explicitly.
So WF is what you put inside the integral. This is the integral.
Yeah. I'm not sure. I guess Perelman, usually calls this V, I guess. Yeah, but it's like the entropy integrand.
Sorry, what is the last term?
Just N, sorry, the dimension of the space.
Okay.
Yeah, and then so then you also have this again with all the same structure above. You have box star WF is minus 2 tau norm Ricci F minus 1 over 2 tau G squared times U. So again, you have this this nice differential equation, which you can apply some maximum principles to it, but you do have to be careful because of the box star. Box star has this reaction term. has this reaction term of the scalar curvature, but there are some maximum principles, but sort of more importantly, this gives the entropy monotonicity. Well, there are many applications of this one, but in particular, you get the monotonicity of G F tau, which again is just the integral of, sorry, probably writing on this iPad, my script W is not so obvious. But anyways, we won't need it too much. Okay. So like this one is like energy. And this one is entropy. Okay, and so yeah, I mean, I'm not going to. This is not really the point of this talk. There's of course a zillion applications of these monotonicity formulas. I just try to just recall this basic circle of ideas. Oh, did you lose me? No, okay.
I can see and hear you.
Oh, okay, good. Yeah, so we have just these basic monotonicity formulas that sort of underpin a lot of the analysis for Ricci flow. So the point is to sort of extend some of this to the case of generalized Ricci flow. But I don't know, any questions before I move on? Okay.
Can you recall what are the implications of this monotonicity of this entropy regarding the analysis for the Ricci flow?
No, I mean it's sort of like everything. I mean, anyways, it's sort of at the bottom of every important result, like after Perelman, pretty much. I mean, the main one, I suppose, the main applications, the initial applications, maybe is the right thing to say, is the general like kappa non-collapsing, which sort of allows you to take blow-up limits that don't experience dimensional collapse. This was one of the big breakthroughs. And also this, well, it's really the pointwise one that gives you this so-called pseudo-locality. I probably will say something about pseudo-locality at the end. This is sort of a smoothing result that tells you with some sort of very weak bounds characterizing Euclidean space, locally the Ricci flow will smooth out things. So basically you need like an almost Euclidean isoparametric constant and a tight lower bound, like an almost positive lower bound for the scalar curvature. And then you can show that the Ricci flow smooths things out locally. That's this pseudo-locality. I maybe will say something about this at the end. Is it okay? Okay. So yeah, so I want to sort of extend this circle of ideas now to generalized Ricci flow, which just recall, here we have GDT is minus twice Ricci plus 1/2 h squared, and dBdt is minus d star g h, and here h is h naught plus dB, and h squared xy is just the inner product of ixh iyh. Okay, so this is the generalized Ricci flow, and well, maybe I sort of also just recall this sort of basic point that so nabla. Okay, yeah, I don't know. I already used nabla above for Levi-Civita, but anyways, I won't use this notation too much, I guess. Nabla H is Nabla plus 1/2 G inverse H. This is like the unique metric compatible connection with torsion H. Oh, I also realized I forgot to write down DH naught is 0. Sorry. Yeah, and so this connection has torsion H, and we can so this has a Ricci tensor, which we could call Ricci Nabla H, and the generalized Ricci flow is equivalent to ddt of G minus B is minus twice Ricci Nabla H. So somehow the curvature of this connection captures these flow equations. Okay. And point is, yeah, this Ricci has a skew part and a symmetric part. The symmetric part is basically this one. The skew part is this one. And well, so but the sort of bad news is that, well, you might naively say, well, okay, I know this connection is somehow relevant, and I'd like to extend this scalar curvature monotonicity, so I could try to compute the heat operator applied to the scalar curvature of this connection, which is that scalar curvature is just R, the usual scalar curvature minus 1/4 norm H squared, but it equals something not useful. I don't really want to bother to write it down. You can compute it, but it's kind of, you certainly cannot get an estimate out of it. It's certainly not positive in general. So it's somehow the wrong thing if we want to try to generalize, if there's going to be a generalization of the scalar curvature monotonicity to this equation, to this system. So the key new ingredient is a sort of further parameter. So this is this dilaton flow. So we let B, a family of smooth functions on the manifold, solve the following. Solve that if I apply the heat operator to phi, I get 1/6 norm H squared. So I'll say a few words about where this comes from. But at first blush, okay, so let me just make a remark.
Sorry, what is the thing in the denominator? I missed this.
That's a 6.
Oh, okay, thank you.
Yeah, that's a 6. So I make a remark is that, of course, generalized Ricci flow is known to be it's like RG flow, is renormalization group flow for a certain sigma model with this torsion H involved. And some, well, I mean, the role of dilaton in Ricci flow even is kind of a delicate thing. So like, I think Perelman, of course, brought it to everyone's attention with this, so like in this F functional, of course, this is basically also like string action. And then you think of U or e to the minus F as like the dilaton. And he attaches this very different PDE for the dilaton and gets all these beautiful formulas out that I'm not sure. And if these are motivated by the math physics point of view, The point is, though, this is of course like a forward heat equation, and it is suggested. My understanding is that this is suggested. So generalized Ricci flow is the same as this RG flow for a sigma model, which suggests, at least in some formulations, which suggests the dilaton flow. So in some sources, you look at, they'll express generalized Ricci flow not exactly like this, but in a gauge with an extra gauge parameter coming from this function phi, which then satisfies a gauge modified version of this flow. But of course, the point is that you can gauge it out. So just to think about generalized Ricci flow, you don't really have to bother with this extra term, with this extra dilaton, but it turns out you should. So the dilaton flow is very important. And actually, so for me, what I think is a nice question that I don't know how to answer is how to motivate this in a so how to motivate this dilaton flow mathematically. I mean, with all due respect to the renormalization group flow point of view. I mean, I just mean sort of, I don't know, in like an elementary, maybe analytic way, as opposed to with like Feynman diagrams and whatever. Maybe the better way to state it is that I don't really understand how it suggests this dilaton flow, and then I would like to understand it in a more perhaps elementary way. But okay, how does this dilaton flow play a role? Well, I have to define two more curvature quantities. So given sort of the data of generalized Ricci flow MNGH, and also now a smooth function phi, I'm going to first of all define this sort of weighted scalar curvature in the following way. So RH phi is the usual scalar curvature minus 1/12 norm h squared plus twice Laplacian phi minus norm grad phi squared. So this is basically the same as the one above. It's just we have this extra 1/12 h squared term. But of course, it's also worth pointing out that this 12, this 1/12 is of course different from this 1/4. So it's not even sort of like weighted scalar curvature of this connection in the classic sense. But you can, so this has appeared earlier. In work of Bismuth. Again, via like a Lich-Nervitz formula for spinors. Maybe I should say weighted Lich-Nervitz. Where again, you think of phi as an exponential weight on the volume form. Okay, so it's some kind of H-twisted weighted scalar curvature, and then we also get this kind of Bakary-Emery type curvature. So this is a little bit easier to motivate. So what's the sign? Minus 1/2 E star GH plus I grad phi H. So again, without the phi, this is just the Bismuth-Ricci tensor. But it's sort of like a Bakary-Emery modification. So we have this Hessian phi term, which is kind of, well, it's an infinitesimal gauge term, sort of for the symmetric part, for the metric, and then ditto, this term, in a sense, is also interpreted, has an interpretation as a kind of as an infinitesimal gauge symmetry, in this case by B fields. It's like the B field action. Okay, but anyways, we don't need to sort of bother with that. The point is, the first theorem is that if we're given MN GT BT, a solution of generalized Ricci flow. So maybe I don't specify the H naught, but and phi t, a solution of the dilaton flow. Then if you apply the heat operator to this weighted scalar curvature, you get twice the H twisted Bakary-Emery Ricci curvature squared. Okay. So I'm not going to prove it. I mean, it's an easy calculation once you know the right thing to do, basically. But yeah, so of course, this has some immediate corollaries. Maybe I don't restate everything, but like the minimum of this quantity RH phi can only go up. So that's immediate from the maximum principle. And so furthermore, if RH phi is bigger or equal to 0, then either GH phi defines a generalized Ricci soliton which just means that this Ricci H phi is 0. Or there exists G prime H prime phi prime such that the scalar curvature is strictly positive. And again, this positivity of this scalar curvature is somehow related to vanishing theorems for sections of some spin bundle by this Lichtenavich formula. So is this statement clear? So, okay, I maybe make a few remarks. So this even sort of extends the classic scalar curvature monotonicity for Ricci flow. This had already appeared. So what do I mean by this? Here, again, you just have dT is minus twice Ricci. But now the dilaton is just a forward heat equation. So box phi is 0. So there is no H. So the dilaton flow is just a forward heat equation. And then what the result above is saying is that you apply the heat operator to the weighted scalar curvature, and you get twice the Bakary-Emery, the phi Bakary-Emery Ricci squared. And then again, there are rigidity corollaries, positivity corollaries, etc. This is previously known, but I think somehow well, I'll sort of take it a bit further than it had previously been taken. I mean, somehow I think it was derived in the context of wanting to understand solutions to the heat equation. But this sort of RG flow point of view gives kind of a different point of view on what this really is, kind of, I guess you'd say. That being a dilettante. So a further remark. This can be extended in various ways. So the first is like in all of these formulas, it's not really phi that shows up in all these curvatures, it's really d phi. So you can instead of the dilaton, you can in fact couple to like a closed one form. So you can define R H alpha is R minus 1/12 norm H squared minus D star alpha minus norm alpha squared, where D alpha is 0. And you need sort of a different dilaton flow. So DDT alpha is now the like Hodge Laplacian for alpha, the time-dependent Hodge Laplacian, plus 1/6 norm H squared. Sorry, a D of, not, let me rewrite that. 1/6 D norm H squared. And then again, and of course, yeah, so to connect with before, of course, alpha's d phi is one class of solutions. But then what you can prove is you apply the heat operator to this R H alpha, and well, you get twice magnitude Ricci minus 1/4 H squared minus 1/2 D star H plus I alpha sharp H. Oh, sorry. And just say plus a nabla alpha, and then plus norm D alpha squared. In fact, you get an extra positive term. So you can still get a monotonicity formula coupled to a one form instead of just a scalar field. And again, I just wonder, how does this relate to, I know there's supposed to be this circle of ideas that the dilaton is somehow related to a divergence operator. And if maybe, well, maybe this is somehow related to that. Maybe the point is not really that you couple to a scalar, but it's really like a flow of divergence operators. So somehow you can identify divergence operators with vector fields, I guess, and so maybe also with one forms. But so, yeah, I just wonder if
maybe I can comment on that on that, or rather comment, well, or maybe just ask something. So as far as I know, this promoting phi to a closed one form of alpha, that this is part of this going into this generalized supergravity story or modified supergravity stuff, which is, as you were saying, like it's like some special class of divergences which do not come from a scalar field. And what I want to ask is that, like, in general, there is, you can even generalize it a little bit further by adding apart from this alpha, you add a killing vector field on your manifold for the metric. And then the condition is that alpha is no longer closed, but it's d of alpha is the contraction of the killing vector field with H. And
Okay.
and the second condition is that that the field is killing, and this should be still a slight generalization of this, I think. And I just wondered
I
if
see. No, I never considered that. Maybe you can show me after. Yeah, that's interesting.
Do you need actually alpha to be closed for this formula to hold?
Oh, yeah, sorry, right. What I wrote, yeah, sorry, right. What I wrote is,
So I would expect that your alpha is the plus part of a
no,
divergence
I
operator.
guess, sorry, I guess not. Yeah, I think.
So this means that in particular, it is, I mean, it incorporates this thing that you were saying, Friedrich. So it's the most general, I mean, you think of the divergence operator, and this is just the general Ricci flow formulated for the B plus, say, and then this alpha is the plus part of the divergence operator minus the remaining divergence. So
I see. Okay, thank you.
Okay, yeah, and yeah, just to confirm, yeah, the result is correct without it being closed. Yeah. But you're saying without it being, it already captures what Friedrich's saying? Is that what you're saying?
So what I'm saying is that you could consider this as a flow for a generalized metric and a general divergence operator with no conditions. Of course, you can impose that the divergence operator is compatible with the generalized metric in the sense that the difference between the remaining divergence and that given divergence is it's an infinitesimal isometry. And this is the condition that Friedrich was mentioning, that the vector field is killing and D of the one form plus the contraction of the vector field with H is 0.
I see.
Also, you can impose further conditions on the divergence, and maybe this gives you enhanced properties, but a priori this is, I would expect this to be general for arbitrary divergence. This is to be what you were saying, that, and this alpha needs to be identified not with the divergence, but with the plus part of the divergence.
I see. Okay. Well, that's very interesting. Okay, yeah. Yeah, maybe I just say in words, maybe it's not quite worth going into it, but this monotonicity holds for a more general class of flow. Well, so basically you can consider generalized Ricci flow where this H is direct sum k equals 1 to n hk, where hk is a degree k form. And a similar PDE. Let me just sort of, for simplicity, or just write down dg dt is minus twice Ricci plus 1/2 h squared, and then dh dt is the Hodge Laplacian acting on h, and dh is 0. And then, yeah, and so you get a similar, well, okay. D phi dt is Laplace phi plus sum k equals 1 to n ck norm hk squared. So there are some constants that have to be chosen. And then you get a scalar curvature monotonicity. So for this RH phi is scalar curvature minus, again, sum k equals 1 to n ck prime norm h squared plus twice Laplace phi minus norm grad phi squared. Then maybe I just say that the heat operator applied to this thing is bigger or equal to 0. You can kind of guess what it is. But indeed, this will have a sign. It's just a sort of formal adaptation of the first calculation. And this seems to capture some other, well, this class of PDE seems to capture some other flavors of generalized Ricci flow. So for instance, this includes Ricci-Yang-Mills flow, where H is really like a two form. It's like the bundle curvature. And also there is this what's called like modified Ricci flow of List from a while ago, where H is a one form, an exact one form. But I mean, I think for these are sort of low degree cases, two forms, one forms, but I think there are interesting examples for H of high degree.
So maybe, I don't know if you explore this, or I don't know if maybe this is a question for free, but can this be interpreted as the natural renormalization group flow for type 2 with Ramon fluxes? Like these polyforms typically are thought of in type 2 string theory as Ramon fields. So there are spinors for tangent plus cotangent. And I wonder if this...
I don't believe that's true, right? Because I don't think the pure degree parts aren't closed by themselves, are they? I think, right? You have more like this.
Because they are close for the twisted differential.
Oh. Yeah, I'm not sure if it. Yeah, but that's interesting. I don't know. You're saying this like DH is F wedge F, you interpret as some twisted.
What I'm saying, if you have, so the way that these polyforms appear typically, or at least in type 2 string theory, they represent some fields which are called Ramon,
yeah.
which are spinors for the indefinite pairing, the classical spinors in general geometry.
I'm not really sure. It might be that. I mean, I don't remember this. How do the equation look like there? But they have roughly the same form, so probably it's related to some in some way. But I don't remember more details. Sorry.
Okay, so let me just make one more remark about kind of another case, and this is also more or less how we found this. So you can look at the generalized scalar Ricci flow. So there's some point is in the generalized scalar Ricci flow setting, there are some interesting or sort of canonical choices of the dilettante flow. So again, maybe just to emphasize, like in this general setup, I have some solution to generalized Ricci flow. It has nothing to do with phi. I can pick any initial data for phi I like. If the initial data for phi is sort of a free parameter in this. And so I get, in a sense, this infinite dimensional family of scalar curvature monotonicities depending on the initial choice of phi. It's totally decoupled from this. Or I guess I should say it's kind of like one-sided decoupled. I mean, these don't depend on phi, but of course this depends on the rest of the data. But anyways,
sorry, related to what you were saying, does it have any meaning to take then phi to be localized, like to be a bound function in some region of the manifold? Does it mean anything special?
Yeah, I mean, I think this is the kind of thing you would want to do, but yeah, well, I mean, this is the kind of thing, of course, that you do, like, so for these applications, like for pseudolocality and all of these Perelman applications of these conjugate heat operator monotonicities, the point is to, usually select like a delta function or near delta function forward in time, and then it kind of flows backward in time to tell you something. But yeah, I think something like what you said, maybe there may also be some way to use it in that way. Yeah, I think so. But yeah, so let me just briefly recall a generalized scalar Ricci flow. So so here the data that's flowing is like GT, BT. I'll let everything flow. And then you have these two compatible complex structures, IT and JT. So just very quickly, the PDE, the Ricci flow part is the same, or this is just generalized Ricci flow. And then, but these two complex structures are also flowing. So I flows by the Lie derivative with respect to the I Lie form. And then ditto J. So dJ dt is the Lie derivative with respect to the J Lie form of J. So I write it in this particular way. And so a special case is the so-called symplectic type case. Where, for instance, you assume I plus J is invertible. And in this setting, the reason it's called symplectic type is that there's this canonically associated symplectic form, which is minus twice G I plus J inverse. So this will be a closed form, a closed non-degenerate two form. And well, there are some hints that sort of this symplectic volume, if you like, is sort of, well, it's certainly relevant to generalized scalar geometry. And so you can define a dilaton by the top power of this F plus is what you mean by e to the minus phi dvg. So you think of this equation as defining phi. Oh, of course, phi you can write explicitly then. This is 1/2, if I got the signs right. Log determinant I plus J. Okay. So yeah, and then, well, the point is that with this setup, then this box phi is 1/6 norm h squared. And also basically because phi is not arbitrary, it's sort of, well, it's explicitly determined by the C0 data of the generalized scalar structure. Then the scalar curvature quantity has some kind of, I suppose, slightly more classical meaning. In any case, it's completely determined by the generalized scalar structure itself. This phi is not somehow extraneous. Yeah, and basically in this joint work with Vesti basically figured all of this out. I mean, well, figured that the relevant scalar curvature had this monotonicity property, and that this was the PDE satisfied by this volume weight, and it was obvious then that it worked in general. So, yeah. So yeah, so I guess the point is in the generalized scalar Ricci flow case, in some settings, even this can be sort of generalized a bit. You have some kind of geometrically meaningful choices for the dilaton flow. And again, just a sort of general question, like in these other settings in pluriclosed, whatever, is there a meaningful choice of dilaton flow?
So is this identity true? Yeah, okay. I don't know even what I mean by that. Is there something like this for an arbitrary generalized scalar Ricci flow, or is something?
Not quite. So basically the more general statement, hold on, let me just, yeah, so I guess more generally, if you have one of your complex structures determined by a family of closed spinors, d psi, so d psi t. There's a lot to prove here. If your flow, let me call it like J1 psi t and like just J2 t. Maybe that looks weird. The point is I only really assume one of them is determined by a closed pure spinor. That's what you have in the symplectic type case. Like F plus is one of the spinor, is the spinor. E to the IF plus is the spinor you need to define one of the GC structures. Then you define a function. Yeah, sorry, I switched from like phi to psi, but anyways, you define phi to be, yeah, again, I probably get the sign wrong, but it's basically the log of this Mukai pairing of psi with itself compared to the volume form.
This Ricci potential.
Well, this is not the Ricci potential. Yeah, this is a super delicate point. So this is like this partial Ricci potential. Here, let me actually give it.
Yeah, like the difference of the two.
Yeah, exactly. So yeah. Sorry. Let me say slightly less generally. So if they're both defined by closed spinors along the flow. Sorry, sorry. The notation I am writing is bad. So like psi 1, psi 2. So suppose they both are. Then you get this like phi I, you get these two phi i's, which are where you compare the Mukai pairings to the Riemannian volume. And again, the signs cannot be trusted in what I'm saying. And both of these satisfy the dilaton flow. Both of these satisfy it. And then the actual Ricci potential is the difference of the two. What we usually call capital phi is phi 2 minus phi 1. And then just obviously as a consequence of this, right, you just get that box phi is 0. And this is like, this hypothesis that they're both determined by global closed pure spinors is of course very special. So like the canonical, these like generalized canonical bundles have a holomorphic section, have a sort of like generalized holomorphic section. So it's kind of like a Calabi-Yau type case. And then this statement is generalizing like the basic fact that along Kähler-Ricci flow, and when C1 is 0, the heat operator on the volume ratio compared to a holomorphic volume form is just 0. This is just like a generalization of that fact.
But still, if you have a generalized Kähler manifold, then locally you can choose these spinors.
Yes.
So I wonder if this gives you a local factorization of the heat equation for the Ricci potential, which is useful. It would be just a local thing.
I mean, locally, yes, definitely. I mean, yeah, so somehow this calculation is strictly local. So, I mean, even if you only have these defining spinors locally, yeah, you can do it. But I'm not sure, well, I mean, I don't know how useful that is. Like the general formula for like the evolution, for instance, of the volume form along Ricci flow, of course, has some more complicated terms. Has some background geometry terms is the point. Well, yeah. Okay, so
sorry, may I ask a question about the previous red stuff?
Mhm.
Just clarification, if I understand correctly. So what you are saying is that if the if G, B, I, and J satisfy these black equations,
Yeah.
and you construct in the symplectic type phi in that way as a log of that, etc., then it satisfies that Laplace, box on F is 1/6 over H squared. Is that the claim?
Yes, exactly.
Okay.
Yeah. And then I don't write down the rest. Of course, then you have the scalar curvature monotonicity. Yeah.
Right.
This is
Right.
the point is you have this meaningful solution of the dilettante flow.
Okay. Okay. I see. Thank you. Oh, I see. Thanks.
Well, maybe not meaningful, but just somehow concrete solution in terms of the given data is the point.
Thanks.
Okay, yeah. So I don't know, anything else? I'm going to sort of switch gears at this point. Okay, so I want to say a few words now about these like Perelman type. Oops. Monotonicities. So recall, I mean, I said at the beginning, so we have a solution generalized Ricci flow, we have the heat operator, and then the conjugate heat operator in this setting looks like this, a minus ddt minus Laplacian plus the scalar curvature minus 1/4 norm H squared. It basically has this sort of classic Bismuth scalar curvature as this reaction term. And again, this is sort of prevents you from really taking it very far because you have no understanding of this term. So in Ricci flow, knowing without this H term, knowing that this R is bounded below is an important point in applying this, in using this conjugate heat operator. It's an important part of the analysis. But so there's sort of a further kind of miracle to this story that kind of ties all these things together, that again, it kind of comes almost a little bit from this picture where you sort of realize that the dilaton, I mean, again, you think of this dilaton as an exponential weight, as a volume weight. So what's the point? We define a weighted conjugate heat operator. So formally, all this means is I want to take ddt, the integral of, say, u and w are just some arbitrary functions on space-time. And instead of just putting the volume, I'm going to put the weighted volume. Okay, so I treat this dilaton flow as a weight on the volume. And then just sort of by definition of what we mean by conjugate heat operator, you get W box U minus U box star W, sorry, box star phi. I decorate it with a phi, e to the minus phi dVg. And then sort of the amazing point is that you can just compute what this box star phi is, and it's minus ddt minus Laplace plus the h phi, a scalar curvature. Oh, I forgot one term, sorry. There's a first order term. So you get the backwards heat operator, you get a first order term in terms of the gradient of phi. So this just acts on functions in the usual way. And then your zeroth order term is exactly this scalar curvature, which now is bounded below. So now we have this sort of naturally, yeah.
Is there a norm square or something of this gradient of phi?
What I mean is grad phi f is like inner product.
Oh, okay, I understand. Thanks.
Yeah. Yeah. So yeah, so you compute conjugate heat operator with this weight, and then sort of amazingly this weighted scalar curvature pops out. And also it's kind of also rectified this difference between this 1/4 and 1/12. Somehow this is, again, it's maybe like the reason for the 1/6 is that this works out in this way. But it's, of course, some hocus pocus. But yeah, so thinking about integral quantities, not in terms of the Riemannian volume, but in terms of the weighted Riemannian volume, it sort of suggests this new operator. And then, yeah, and then I just sort of point out some monotonicity, some further monotonicity formulas that hold. So now we fix, or sorry, let me point out one more basic formula. So for a general,
Wait, I'm a bit confused. So the third term is 2 gradient of phi? Oh, okay. You wrote what this means. Gradient of phi applied to F. Okay. Sorry.
For a general function, these operators, the sort of classic and weighted heat operators, have this simple relationship. So the box star of u e to the minus phi is just box star phi u e to the minus phi. So somehow you just pull this weight out of this operator at the expense of weighting the operator. Anyways, this is some basic point we'll use in a minute. But so, I think we've previously discussed here how generalized Ricci flow has this gradient flow interpretation, and there is a sort of pointwise estimate underneath it. And those have a nice interpretation using this weighted operator as well. So we fix u, again, is e to the minus f, and ask that it solve the conjugate heat operator, conjugate heat equation, weighted conjugate heat equation. Well, then we can combine all these different things in the following way. So we apply the weighted conjugate heat operator to a certain weighted scalar curvature, but we have to kind of further adjust the weight. So it's the F plus phi scalar curvature times u, and you get minus twice the Ricci, again weighted by F plus phi squared times u. So we have this nice one-sided differential inequality that sort of pops out of this picture, and even this alone has a number of consequences. So let me just make some remarks about this. One is that this implies, again, this sort of F monotonicity. Where now F GH, we call it psi, is this string effective action. Oh, sorry. So it has this form, but of course it's also, just like before, this is also just like RH psi e to the negative psi dVg. And the point is that already we kind of knew this formula where box star e to the minus psi is 0 gives a monotonicity. The point is you kind of think about a solution to this equation in a different way. So like what this is saying is that you interpret psi as f plus phi, where box phi, so phi is a dilaton flow, and f satisfies this weighted conjugate heat equation. And the sort of thing that ties it together is this basic formula. So the point is, with things set up the way I did, so phi is a solution, the dilaton flow, e to the minus f solves this weighted one, then you know then e to the minus psi will solve the classic conjugate heat equation. So it's kind of a way of breaking up a solution to the conjugate heat equation into a solution to the forward dilaton flow and then this weighted conjugate heat operator. And again, even this point of view is like a little bit different for Ricci flow. I mean, it's sort of telling you kind of one of the points of Perelman's formulas is that this choice of F or this choice of solution to the conjugate heat operator is kind of arbitrary. You have this infinite dimensional degree of freedom. You localize, you pick some delta function at a point. But this is saying we kind of have 2 degrees of freedom. There's a backwards flowing degree of freedom and a forward flowing degree of freedom. You can pick this phi, the initial data for this phi, like arbitrarily, and still get a monotonicity formula. Yeah. Actually, yeah, maybe this is the only real remark I wanted to make. Or I kind of just bundled it all together. But anyways. Okay, and then also, we can get something like the Schrinker-Harnack inequality. So this U, I now normalize in a different way. So it's e to the minus f over 4 pi tau to the n over 2. And I ask that box star phi U is 0. And again, I define this sort of entropy integrand WH psi is tau RH psi plus psi minus n. And then again, with this same setup above, and here again, you think of tau as some kind of backwards time parameter. So then box star of WH F plus phi U is the following. So it's minus 2 tau norm Ricci H F plus phi minus 1 over 2 tau G squared times U, and then plus 1/6 norm H squared times U. So I mentioned this formula, I don't know, at the very beginning, in the case of Ricci flow. there's this amazing entropy monotonicity, which has many applications, many analytic applications. This one, of course, well, it's not immediately monotone. We have this one nice negative term, but then unfortunately there's also this positive term. And it's something of a mystery. I mean, sort of this dilaton flow. So again, maybe I just make a remark. This term prevents the immediate applicability of this formula but these can be recovered when an upper bound is known for phi. So phi, of course, let me just write it down again. Box phi is 1/6 norm h squared. Phi min, of course, goes up. So you always have this lower bound for sure, but an upper bound is less clear. But you do have such a bound. Well, in various cases, I'll just say, like, for instance, for blurry closed flow, say when you know the cohomology class of H is 0 or something like this. So there are cases where some kind of fairly general broad cases where you can prove that this phi is bounded above. And the reason is because, well, the point is, of course, you want to apply this formula, but you have this bad term. You can kind of add some terms involving phi to cancel this one out. It's somehow exactly involving the evolution of phi, right? Somehow using the dilaton flow itself, you can sort of modify this by some further terms and kill this term off. But then you need to make sure the phi is actually bounded to get something useful, at least at first blush. That's how it seems. But at least in some important cases, you can do this. You can get this bound for phi. But okay, yeah. I think probably it's best. Maybe I just stop there. So yeah. So thanks for your attention. I don't know. Yeah. Do you guys have any more questions? Or? Yeah, okay. If not, that's fine too. Let me